Today we have a theorem which states that if a function is from a set A to a set B, and E and F are subsets of our codomain B, then A states that taking the inverse function commutes with taking the union. So the inverse function of F applied to the set E union F is F inverse E union F inverse F. Part B states that the inverse function applied to the set E intersect F. Also, the inverse also commutes with the union in the sense that this expression is equal to the set F inverse E intersect set F inverse F. Third part of our theorem states that if F is a subset of E, then I can consider E set minus F. And F inverse of the set minus operation, F inverse also commutes with the set minus operation in the sense that F inverse of E set minus F is F inverse of E set minus F inverse of F. Okay, so to prove this theorem, we need the definition of F inverse, which is not a function per se, as you might be used to the term. This is going to be a function on sets. Okay, so let's draw a picture here. So if I have the set A and I'm mapping this via the function F to a set B, okay, then this is the traditional function what we're used to. So F will map a point little a to a point F of A, which belongs to B. Okay. However, F inverse is only defined as a function if F is bijective. Okay. And moreover, if F is injective onto its image, so if F is 1-to-1, then we can define an inverse function on the image. So note that if F is 1-to-1, then what this means, you'll forgive me for erasing part of the theorem for a moment. So if F is 1-to-1, this means that F assigns distinct values to distinct values. Okay, and so in particular, if I look at X, or let's say small a, if I look at A is going to get mapped to F of A, and moreover, if I have B, which is not equal to, this is confusing, sorry, if I have A prime, let's say, a different element of A, which is not equal to A, this is going to get mapped to F of A prime, and these values are distinct, okay? So, what I can define, we can define a function in the traditional sense of a function, which goes from F of the set A, so the image of A, which is a subset of B, okay? So this is basically, pretend that F maps all of A to maybe some subset, let's say F of A, some subset of B, consisting of all the points in the range of F. Then there's a well-defined function, F inverse, from the image of A under F back to A, which basically assigns F of, let's say, little a here gets mapped to A. And this is a well-defined function, F inverse, because it maps, it doesn't map to, it doesn't map F of A to two distinct values, okay? So the reason why this is well-defined is if this gets mapped to two different values, okay? So if F of A gets mapped to two different values under F inverse, then this would imply that F of A prime is equal to F of A, which contradicts the fact that F is 1-to-1, okay? So this cannot happen. basically. And we're left with a unique assignment that for each point in our image, we have a unique point in the domain which gets mapped to that image, and so we can define the inverse mapping. And this is what you traditionally think of when you think of an inverse function. But this is actually not the inverse function that's being referenced in this theorem. So let's discuss what is being referenced. Well, okay, so given f from A to B, we can define a map, which we also call f, but it's from the power set of A to the power set of B. Okay? And what it does is it maps a set, let's say, we've already used E and F, so let's say C, okay? So if C is a subset of A, all right, C is going to get mapped to the set F of C, which is, by definition, the set of all little b in capital B such that F of C equals B for some C in the set C, okay? So a little bit of a complicated definition, but essentially what I'm saying is that I'm taking all the points in this set C, and I'm looking at where F maps them. So let's redraw the picture here. So I have a set A, and then some smaller set C, and I have this mapping F from A into B, and so F is going to take each point of C, and F is going to map each point of C to some point of B. And so if I look at the entire set C, where that gets mapped by F, maybe that's some weird set over here, then, okay, so this entire set C gets mapped to all these points in the set C get mapped to this set, which we're calling F of C, okay? So the image of the set C under the mapping F, okay? So we're going to define the inverse function in a similar way, okay? So this is where I want to be really careful here, okay? So I apologize, I don't have enough space, so let me erase the theorem, and we'll come back to it in a moment. So I need to define what F inverse is first. Okay, so again, I have the set A, and it's being mapped via F to the set B. Okay, now if I want to define F inverse of a subset of B, so let's say that E is now a subset of B, okay? Then I'm going to define F inverse of E. Okay, so if we let E be a subset of B, then F inverse of E is defined to be the set of points A in our set A such that F of A belongs to our set E, okay? So let's look carefully at this definition, okay? So essentially I'm saying F inverse of E is this set, which could look pretty weird over here. So in this case, I'm going to draw it as kind of a weird looking set. Here's F inverse of E. And the point is that F inverse of E is the set where any point in this set gets mapped via F into E, okay? So it's the set of all points in A which get mapped by F into the set E, okay? So this is the definition of F inverse of E, all right? So now, with this definition in our hands, and I'm going to rewrite it at the top of the board, let's go ahead and prove this theorem. Okay, so we have F is a function from A to B, and we have that F inverse of E is the set of A within A such that F of A is in E, okay? Where if E is a subset of B, okay? All right, so now let's prove the first part of the theorem. So A states that the inverse function commutes with the union. So F inverse of E union F is equal to F inverse of E union F inverse of F. Okay? All right, so the proof, again, these are sets. By definition, these are sets. These are sets, subsets of A. Both of these are subsets of A. So to show that these sets are equal, we need to prove both sides of the set theoretic equality. So first, let's prove this direction, okay? So let A belong to F inverse of E union F, okay? So then by definition, we know that, that F of A must belong to E union F, which tells me that F of A is in E or F of A is in F by definition of the union, okay? All right, and so in this case, we have that if F of A belongs to E, then by definition, F inverse of E contains A. All right? So if F of A is in E, then the set F inverse of E contains A. This is again by the definition. Recall that we defined F inverse of E to be the set of all A within A such that F of A is within E. Here I have F of A within E, so therefore my point A must belong to the set F inverse of E. So that's this case. Or in this other case, this other possibility, F of A is in F, well then we just have that F inverse of F contains A. And so what this means by definition of the union again is that A is contained in F inverse of E, or, which is the union symbol, F inverse of F. All right, well that's exactly this direction of the set theoretic inequality. We've shown that the arbitrary element of this set must belong to this set. So therefore this set must contain the set on the left. Okay, then let's look at the other direction. Okay, so let A be within F inverse of E union F inverse of F. Then we know by the definition of the union that A is in F inverse of E or A is in F inverse of F. Okay? And in the case that A is in F inverse of E, okay, well in this case, then we know by definition that if we look at the definition of F inverse of E, this means that F of A is in E, or F of A is in F, which is this expression. So this implies F of A is in E by definition. This expression, A in F inverse of F, implies F of A is in F by definition. So we have that F of A belongs to E or F of A belongs to F. Well, this just means that F of A belongs to E union F, by definition of the union, again. And now we can apply the definition of the inverse function, and this tells me that A belongs to F inverse of E union F. And voila, this proves the other direction of the inequality. We've taken an arbitrary element in this set and shown that it must belong to this set. Therefore, since we've proven that both of these sets contain each other, they must be equal. Okay? That proves part A of the theorem. Now, part B. We want to show that the inverse commutes with the intersection. So F inverse of E intersect F is equal to F inverse of E intersect F inverse of F. So again, we're going to apply the same reasoning here. So first, let's consider this direction of the set theoretic inequality. So let X belong to F inverse of E intersect F. by definition, this implies that f of x is going to belong to E intersect f, which tells me that f of x belongs to E and f of x belongs to f. F of x belonging to E tells me that x belongs to f inverse of E. And similarly, f of x belonging to f tells me that x belongs to f inverse of f. And now we conclude that x belongs to both of these sets, therefore it belongs to their intersection. F inverse of E intersect f inverse of f. Great. Okay. So that proves this direction of the set theoretic inequality. Okay? Let's do the other direction. Okay, so let x belong to f inverse of E intersect f inverse of f. Then x belongs to f inverse of E and x belongs to f inverse of f by definition of the intersection, which this expression tells me that f of x belongs to E, and this expression tells me that f of x belongs to f. So therefore, f of x belongs to E and f, so E intersect f, and therefore x belongs to f inverse of E intersect f. And voila, we have the reverse direction of the inclusion. So that proves part B of the theorem. Let's look at part C. So part C, and I guess we should mention that f and E are both subsets of B. F and E are both subsets of B. So for part C, we want so if f is a subset of E, then we want to show that the inverse commutes with the set subtraction. So f inverse of E set minus f we want to show is equal to f inverse of E set minus f inverse of f. Okay? So the proof of this claim, same logic. Let's prove this direction of the set theoretic inequality first. So let x belong to f inverse of E set minus f. So this tells me that f of x belongs to E set minus f. So therefore, f of x belongs to E and f of x does not belong to f. Let's recall the definition of the set subtraction real quick. So E set minus f is defined to be the set of x in E such that x is not in f. Okay, so the picture here is here's E, here's f, then E set minus f is everything in E which it does not belong to f, okay? All right, so kind of we're cutting out f from the set E. And another way to describe this would be that E set minus f is equal to E intersect f complement. Okay, so f complement by definition, recall that f complement is the set of all x in E in our larger space B such that x is not in f. Okay, so these are just three different sides of the same coin. So basically, yeah, so saying that an element belongs to E intersect f complement is the same thing as saying the x belongs to E and it does not belong to f. So that's exactly the definition of E set minus f. Okay, so that's what allows me to pass from this line to this line here, just using the definition of the set minus. Okay, so f of x is in E and f of x is not within f. What does this tell me? This tells me that x belongs to f inverse of E, and if f of x does not belong to f, then x cannot belong to f inverse of f. Okay, So this is the key step, okay? So let's unpack this. So if f of x does not belong to the set F, okay? So remember that x is in F inverse of F, this implies that F of x belongs to the set F by definition of F inverse of F. So if x is in here, then F of x is in the original set F. Well, I can take the contrapositive of this statement. So remember, P implies Q, logically equivalent to not Q implies not P. So negating this statement, I have F of x not within F implies x not within F inverse of F, okay, which is precisely this statement here, passing from this line to the next. F of x not within F implies x is not within F inverse of F. Okay, so now we're here. Well, this means that F of x is in F inverse of E and x is not within F inverse of F. So by definition, x must belong to F inverse of E set minus F inverse of F, and that proves the first direction of the set theoretic containment. Now let's do the other direction, okay? So this direction. So let x belong to F inverse of E set minus F inverse of F. This tells me that x belongs to F inverse of E and x does not belong to F inverse of F, okay? So now what can I conclude from here? So this first statement tells me that F of x belongs to E. Now, if x does not belong to F inverse of E, then what can we say about F of x? What we want to say is that F of x is not within, this is an F, apologize. F of x is not within F. So this is what we want to say, but can we say that? Okay, so let's see if we can say that or not. So remember that F of x in F is going to imply that x is in F inverse of F. Okay, so taking the negation of this statement, the contrapositive, we have that x not within F inverse of F implies F of x is not within F. So indeed, we can pass from this line to the next. And then once we're here, well, now let's look at what we have. We have F of x is in E and F of x is not within F. Therefore, F of x is in E set minus F. Okay. So this tells me that x belongs to F inverse of E set minus F, and that proves this direction of the containment. So that concludes our proof of the theorem.